Hello, everyone. Welcome to AWS reInvent 2020. My name is Karthik, and I'm a Senior Solutions Architect in AWS, supporting Amazon.com as a customer. I have with me today my colleague, Huzaifa Igatpuriwala, also a Solutions Architect at Amazon, who will join us for the second half of the presentation. Today, we will be talking about, under the hood, how Amazon uses AWS for analytics and petabyte scale. In today's presentation, we will be talking about history, how we evolved to what we are today, talk about the migration patterns, the current architecture, and evolution, which is key for every architecture on AWS. Okay, let's start with history. To give you a high level overview on the business landscape, Amazon is a globally distributed business. We have users around the world who contribute and interact with this system. In the legacy days, this system had one of the largest Oracle clusters in the world. And this system is being used by multiple teams within Amazon, Prime Video, Alexa, Music, all the businesses. We have SDEs and analysts and machine learning scientists who have plethora of use cases and access patterns for the underlying data. We have about 38,000 active datasets and 80,000 users running about 900,000 daily jobs on this platform. Here's a quick summary of our legacy environment. It's a single fleet that managed all of our data via the Oracle clusters. Back in the day, only one environment due to the massive scale. No separate ETL environment, but this was an ELT environment wherein all the jobs were handled via SQL. We have our source systems on the left, wherein the underlying data stores for them are on Amazon DynamoDB and Amazon Aurora. Then, within the legacy data warehouse, we had multiple services within it, such as workflow web interface, APIs for the workflow, data ingestion, etc. And these services leveraged a combination of Oracle and Redshift to handle the data warehousing needs. The downstream dependencies for these internal services were software applications, reporting systems, and users who interacted with this data. Within Amazon, one of the largest data lakes they own is named as the Andes Data Lake. The top three goal we had when building this data lake was have an ecosystem that scales with Amazon's business. Every day, we constantly add new products to our customers on our website, add more TV shows and live sports to Prime Video, and more. So we needed a data lake that can meet with this ever-growing demand. We also wanted to have an open architecture that allowed evolution. This would give engineers the option to look at the right tool for the right job. With all the services that constitute the data lake, our underlying technology should be AWS services. AWS provides these building blocks that allows customers like Amazon to build and curate services that meet their unique business demand. Now, let's talk about the steps that we took as part of this migration. As you can tell, we had some challenges in our legacy environment. Our data storage and underlying compute were coupled together, which means we could not scale the necessary individual components but instead had to scale up the entire platform. We have Amazon engineers spend hundreds of hours per month on maintenance and patching. That is not a good use of an engineer's time. And not to forget about the expensive licensing and hardware costs. The hardware needs to be pre-provisioned for peak workloads, which means we were paying for our peak costs for the entire year. That was definitely not frugal. So some of the requirements we had for our new platform were business will not stop when interacting with this platform. Peak workloads or not, our customer expects Amazon services to be online 24/7, 365 days a year. Our analytics solutions needed a redesign due to some of the challenges mentioned earlier. And most importantly, we needed a decentralized system. A system that is decoupled to the lowest layer so we can scale individual components when needed versus provisioning for scale. Now let's talk about how we made that happen. This took us about 2 years. It was a huge technical challenge, but it was necessary as part of our evolution. First, we built out our metadata service and governance service. Then, we built a data mover that moved the data from the Oracle system over to S3. S3 was our primary data store or landing zone. And in the new destination, we leveraged new formats versus the old. And regarding the load strategy, We ensured that the data was present in two systems in parallel. This was to ensure data loss does not happen. We intended to run both the legacy and the new one at the same time until we finished the entire migration. This was very hard. However, migrating the jobs was the hardest part. 900,000 jobs was no small feat. We built a query conversion service that helped us convert some of our legacy transforms into the new migrated transforms. Once the data was completely migrated, we disabled our legacy ecosystem one by one and had just one platform, which was our Andes Data Lake. Here are some key takeaways for our customers. Leadership support is a must. It's a much easier approach from top down versus bottom up. Self-service tools and mechanisms are the key for scale. Without this, there's a huge operational overhead for teams that own these ecosystems. The plan to run legacy and new was a decision that was made per our business requirements. So we worked backwards from that to arrive at that decision. During this migration, there was a learning curve for our Amazon engineers. Engineers had to retrain themselves on the newer tools that were leveraged. Downstream analysts and engineers had to redo their reporting and charting. This also meant training for them to learn how to use the newer tools. And then, as always, communication is key. Every change we made were communicated to all stakeholders, and all important decisions were made together. Here at Amazon, we are all owners here. Now, I would like to bring up Josefa to talk about the current architecture.
Hello, everyone. Thank you for joining this session today. My name is Josefa Igatpuriwala, and I'm a solutions architect with Business Data Technologies team within Amazon. My job is to work with teams within Amazon and help them architect solutions using Andes and AWS services. During the migration, my team was involved heavily in helping users from legacy data warehouse to the Andes Data Lake architecture. So today we are going to dive deep into the Andes Data Lake and how it helped us to be successful for our migration. So here's what we built. In our Andes Data Lake, this slide shows how data flows from the source systems to Andes and from Andes to downstream targets. I'm going to be diving deep into the different sections of this slide one by one. For now, let's focus on the box in the center called the Andes Data Lake. The workflow boxes that you see inside on the left were inherited from the legacy system. We kept our workflow systems largely the same and enhanced them to read from S3 apart from Oracle. During the migration, we kept the old system running in parallel and we added a bunch of services to manage the data on S3. These services we call as Andes, which consists of a UI at the top where users can interact with datasets. Users could search and find datasets, modify by adding a column or changing schema. Users could also version and deprecate datasets in a coherent way. These services, apart from managing these datasets on Andes, would also consistently propagate data to downstream compute targets. These services sit at the core of Andes on top of S3, allowing the files in S3 to be used or treated like tables. One of the important things that we also built was the ability to have merge semantics in these datasets. If you worked with S3, you know that data in S3 works in an append only model. You keep adding data to the system, but when you get multiple versions of the same record, they're just sitting across multiple files. This system would build a merged version of the dataset in S3 so that users could do a compute on top of it. And similarly, when we propagate the data to Redshift, it would appear as a merge was being performed in the record. Like I said earlier, these services would make the files on S3 look like tables. So users had the ability to define primary keys for their datasets, and we would use that information to perform the merge on Redshift by deleting old records and inserting new records in their place. All these services helped us to emulate the behavior of the legacy data warehouse for accessing data backed by S3. One of the big pieces of this here was the box in the middle of the right hand side that you see called the subscription service. As changes occurred to datasets on Andes, the subscription service would propagate the data or metadata out to the analytics environment across Amazon. Users could filter on rows, they could pull data onto their local compute, and if they needed more storage, they could just add more storage. If they needed more compute, they could just add more compute. If they preferred Redshift, they would go with Redshift. If they wanted to use EMR, they could go with EMR. We also integrated with Glue, which was a centerpiece in our non relational approach of accessing datasets. Many of you who are aware of the Elastic MapReduce service, which can be used as a delivery platform for analytics. Our integration with Glue helped software engineering teams to access datasets via EMR. Synchronizers for Glue would propagate metadata to the Glue catalog for any new updates or additions on Andes. The last target that we had in scope was Redshift Spectrum. Redshift Spectrum, if you see, is in some ways like Glue plus Redshift. We were able to synchronize data sets where users were also able to use Spectrum along with their Redshift cluster. One of the key things, along with the subscription service, was that it was managed by our orchestration service inherited from the legacy data warehouse. This service knew when a dataset was refreshed and data had been propagated to one of the targets, so that jobs could be triggered on that dataset when we knew data had been arrived on that target. This service sat at the heart of our legacy system, and we integrated and extended it with the new Andes architecture. So once we built all these services and we got them stood up and people started migrating, we were able to disable the legacy Oracle environment and eventually were only running S3 as our backing store and the distributed analytics environment solely on AWS services. So in the first slide, we looked at the heterogeneous sources. Now let's dive deep into that a little more. So what do we support currently? From Amazon Kinesis, data can be ingested in real time or batch manner using Kinesis data streams or data firehose. From DynamoDB streams, users could ingest data at a grain of as low as of a minute. From Redshift and RDS, data could be ingested in a batch manner to Andes. Recently, we also started supporting registration of metadata for datasets in AWS Glue, backed by S3. In this case, metadata was synchronized to Andes based on CloudWatch events. Now let's dive a little more into the Andes metadata service. So Andes metadata service, starting with synchronization primitives. So this is the place where we write the data out to compute targets. We keep track of the data when it arrives and coherently propagate to users' compute. This also has the merge semantics integrated into it, which helps us to mimic the merge logic on the relational database. Next is completion service. Many of our customers wanted to be able to use Glue or Airflow or even custom EMR orchestration, for example, to get notified for a dataset, like when a specific logical partition had been updated. The completion service helped users to coordinate updates from step to step using these different orchestration services. We built the concept of manifest, which is nothing but bundling changes made to many different files together. Basically, a manifest consists of the list of ARNs for the files which are being updated. Manifest also captures the metadata and merge semantics. We partnered here with the Redshift team so that we use the same manifest spec as the Redshift team had published, which helped us to integrate with Spectrum. Access management and governance. We built this abstraction layer on top of datasets to control permissions on who had access to what datasets. Um, don't mind, but this is still like a work in progress for data governance. But we were able to build strong access control for Andes datasets using this abstraction layer. Tracking workflow analytics. We had the ability to perform lineage and track upstream and downstream workflows. This helps us in operational troubleshooting, workflow discovery, and also reducing engineering efforts. And last is the data formats. So even though Andes was built as data format agnostic, Currently, the propagation of the data to downstream targets only happens for TSV and Parquet formats. Let's dive into the subscription service. The subscription service is a very powerful tool when you're thinking about analytics at scale, especially at Amazon scale. There's no one fleet system or solution which could manage compute requirements for all your analytics at scale. We built the subscription service for propagation of data to diverse compute targets in a coherent and consistent way. A subscription mainly consists of two things. First is the contract, which generally has the metadata about governance, who or what kind of access to data is present, security, SLAs, or declaration of how frequent datasets would be updated or what kind of support dataset owners had agreed to provide. Under synchronization, a subscription consisted of synchronization of data and metadata to compute targets, as well as propagate schema changes or perform a data backfill. We're still trying to continuously optimize parts where the synchronization involves large backfills or modification of tables with higher number of columns. All right, let's look at synchronizer targets. So, why did we go with Amazon Redshift? From the legacy data warehouse, we saw this powerful pattern amongst our users coming from diverse technical backgrounds that they had the ability to sit and write queries and get the data that they wanted from our legacy system. Obviously, they had to have the business acumen of data sets, they had to know how to write the SQL, and also understand the data. We wanted to preserve this, and Redshift gave us the power to support that level of consumer requirements. We do support ETL fleets. We know that the difference between an ETL and non-ETL query is a bit fuzzy. ETL queries go through large amount of data scan and they are expensive everywhere. For example, even if you run it on Redshift or on EMR. So along with the transform queries, we also supported ETL queries. Integration with Glue. Like I talked about earlier, software engineering teams within Amazon are comfortable enough to work with EMR, which requires a bit more knowledge apart from just writing SQL. You have to understand the clusters, the data skew, and the administration. And with the option of Glue, software engineering teams had the ability to act on data directly using EMR. We had a team within Amazon who provided shared EMR fleets with orchestration services to make it easier for consumers to use Glue. This was fantastic. We later on merged with this team, and that service is basically considered now as a corporate enterprise resource for running shared EMR fleets. And I'll touch upon that a little more in my next slide. And we've seen great adoption in that as well. We integrated with Spectrum, and it opened a wide range of possibilities where users could query on large data sets without even having to worry about storage on Redshift. So I was talking about shared EMR fleets in my previous slide, and what do we actually provide here? Users have the ability to run queries on Spark via Scala or Spark SQL, acting directly on Andes, thereby creating orchestrated DAG workflows on EMR. Users could build heterogeneous data pipelines and perform data aggregations to bring data to Andes and eventually bring that to their Redshift cluster. Users could also make the data accessible for the analytics stack from AWS and also perform ML on Spark using Scala. Now let's look at some of the metrics that we captured during this migration. We found that purpose-built databases allowed Amazon.com to choose the right tool for the right purposes, and that one size no longer fits all. Under cost reduction, we adopted the pay-as-you-go or pay-for-what-you-use model, and teams reported 40 to 90% of operational cost savings. Under operational excellence, we reduced the peak scaling effort 10 times and the admin overhead with the use of AWS managed services. Under performance efficiency, with the adoption of Redshift for running queries faster and Glue and EMR acting on data directly, teams reported latency improvements of 40% at 2 to 4 times the load. Let's look at what we are going to work on in future. Serverless technologies. We're looking to leverage more and more managed services for both upstream and downstream purposes. Service discovery framework. We'll be focusing on providing service to service authentication and make services available for folks in different or less popular regions. Under compliance, we're looking to automate the part where teams have to remain compliant as per different data regulation requirements. Under optimization, we recently transitioned from a centralized Redshift cluster model to a bring your own Redshift cluster model, and we are striving continuously to optimize compute, storage, and provide cost accountability. For machine learning, we are looking to make Andes interoperable with more and more AWS ML services in near future. That ends my talk for today. Here are some of the resources that I like to share on similar sessions which we've done in the past. I'd also like to share this link of AWS migration playbooks, which may come in handy for your database migration project purposes. Thank you once again for joining with us today. Stay safe and stay well.